Hello chemists and welcome to Bale's Chemistry. In this episode I'm going to talk to you about redox reactions and half equations, where we'll look at redox reactions, how they're made up of different half equations, before I talk you through how to construct half equations and then combine them together to have a full redox equation. This is AQA Specification 1.7 redox and it's on paper 1 of your final exams. The channel's recently hit 200 subscribers, which is fantastic, and if you're watching this and haven't subscribed yet, I'd really appreciate it if you'd consider it. So before we start talking about redox reactions, it's really important that we understand oxidation states and the rules that we follow to work out those oxidation states. If you're not yet sure, go and check out my video. There's a link at the top of the page or in the description below. So a redox reaction involves both a reduction and an oxidation process. This is where the term redox comes from. If we consider this simple combustion reaction, we can see that magnesium has gone from its element, which is an oxidation state of 0, to being combined with oxygen and now has an oxidation state of +2. We can see that it's lost 2 electrons, so remembering our mnemonic oil rig, we can see that this is oxidation. Looking at oxygen then, it started as an element, but it has an oxidation state of 0, and is now bonded to magnesium and has an oxidation state of -2. This means that it's gained 2 electrons. This is reduction. When working this out in an exam, I find it particularly useful to write the oxidation states below, before identifying which one's been oxidised or reduced. It is possible to split apart the oxidation and reduction processes to form 2 half equations, and this is what we're going to look at next. Each half equation will only show the oxidation or the reduction of one of the reactants. A redox equation will be made up of 2 half equations. It's quite common to be asked to write out the half equation for the individual reduction and oxidation processes taking place in a reaction. First, you'll need to assign the oxidation states to each species. This allows you to identify the process as oxidation or reduction. Then you'll need to add the electrons to either the left-hand side if it's reduction and the right-hand side if it's oxidation. In more complicated examples, which we usually see in exam papers, you'll also have to balance the oxygens with water, and then you'll have to balance the hydrogens. In our first example, we're going to look at constructing the half equation for the oxidation of magnesium. Magnesium will go from the Mg atom to Mg2+ ion. We'll start by assigning the oxidation states to the species present, so 0 for magnesium atom and +2 for the magnesium ion. We can then see that magnesium has lost 2 electrons, remembering oil rig, and this process is oxidation. We're then going to add our 2 electrons, placing 2 on the right hand side as this process is oxidation. In this example of reducing chlorine, Cl2 will form 2 Cl- ions. As before, we'll start by assigning the oxidation states, so 0 for the Cl2 and -1 for the chlorine ion. Even though there's 2 of them, we represent the oxidation state for a single ion or atom. We can see that the change then is from 0 to -1, and we've gained an electron, so this is a reduction process. Now it's important to remember there are 2 chlorine atoms, so we'll multiply out our electrons by 2 when adding them. And this time, we'll add those 2 electrons to the left-hand side, as it's a reduction process. There are a few more complicated examples which require you to balance the oxygen atoms present in the equation. We'll start these in much the same way as the last 2 examples, working out the oxidation states for each of the species present. In this case, we'll start with oxygen, which will be -2, but as there's 4 of them, it'll give us -8 overall. Now there's a single negative charge on the MnO4-, so manganese will be +7. The Mn2+ ion in the products will have an oxidation state of +2, as that's the charge on the ion. From this we can see that manganese has gone from +7 to +2, gaining 5 electrons and being reduced. We're now going to add those electrons to the equation, adding 5 electrons to the left-hand side as this is reduction. However, we have 4 atoms of oxygen on the left-hand side and none on the right. We use water to balance out the oxygen, so we'll place 4 molecules of water on the right-hand side to balance them out. Adding water now means we have an imbalance of hydrogen atoms, and to fix this we'll add 8 hydrogen ions to the left-hand side. This is our half equation finished. If we do these 2 final steps to balance oxygen, adding water to the right and hydrogen to the left, the reaction needs to happen in acidic conditions, which provides the H+ ions. Now we've looked at making different half equations, what we can do is combine these half equations together to make a full redox reaction. We take our 2 half equations, an oxidation and a reduction process, and we're going to balance these 2 equations so that the numbers of electrons in each is the same. So we multiply the first one up by 4, so it has 12 electrons, and the second one by 3, so it also has 12 electrons. We can now combine these equations. We take everything on the left-hand side of both equations and put them together, and then do the same for the right. we can see that there are 12 electrons on each side, and these can be cancelled out and then removed. We also have a positive negative ion, and we can combine those two to get an ionic product of Fe2O3. There are some steps that you can follow to combine half equations. Start by multiplying each of the half equations so both have the same number of electrons. Combine those half equations, keeping the species on the correct side of the equation. Cancel out the electrons from both sides, and then combine the positive and negative ions to form an ionic product. In summary of this episode then, oxidation states are found using a set of rules. Redox reactions have both a reduction and an oxidation process. Half equations show these two separate processes. Electrons must be added to half equations. Oxygen is balanced using water and then hydrogen ions. And when you combine half equations, you multiply them up to make the number of electrons the same in each before cancelling them out. Thanks for watching this episode of Bales Chemistry. Click up here for more redox videos and click down here to subscribe.